Hello, kiddos. All right, I'm on my iPad. We are home with a snow day. So it'll be a little bit different. I'm unable to show you things under my document camera because I don't have it because I'm at home. All right, so we're in 7.3. And with your 7.3 notes, we need to get into learning about covalent compounds. Now, the good news is that most of this is going to be review. And so since it's review, I will go a little bit fast through some of it. So if you need to pause and slow down, then that's also totally fine. Okay, so first thing, let's get into covalent bonding. Don't forget that this is between a nonmetal and a nonmetal. So two nonmetals. Sorry guys, I'm trying to zoom this. There we go, where you can still see it. All right, so two nonmetals is our covalent bonding, whereas the ionic is a metal and a nonmetal. So in covalent bonds, you need to remember that they are sharing electrons and they will be in a pair. Because remember, from here on out, everything's in a pair. And covalent compounds will either be polar or nonpolar. Okay, so let's do some more definitions. So we're going to define some of our big words for this unit, and the ones I just highlighted in yellow are review, so I am going to go fast. All right, so covalent bond is a chemical bond formed by the sharing of electrons between two atoms. And these atoms are going to be nonmetals, okay? Now, a molecule is a neutral group of atoms that are held together by a covalent bond. A molecular compound is a chemical compound whose simplest units are molecules. Well, I can't spell molecules, that's an E. There we go. All right, that are molecules. Chemical formulas show the type and number of atoms in the smallest representative unit of that compound. The formula unit is the simplest whole number of the whole number ratio. I know I was forgetting a word. Whole number ratio of ions in an ionic compound. And then the last review vocab word is, or phrase, because two words. Molecular formula shows the types and numbers of atoms combined in a single molecule of a molecular compound. Okay, so that is the review vocabulary. And so what is new to us are these two words, intramolecular forces and intermolecular forces. Okay, so let's talk about those real quick. So intramolecular forces are going to be the forces, there we go, I'm trying to get my pen back. There we go, I got it. Intramolecular forces occur within a molecule. So the intramolecular forces is the force between the hydrogen that is bonded with the oxygen in a water molecule, and or the oxygen to the hydrogen molecule. So those are the intramolecular forces. That is within the actual molecule. It's inside. So the prefix intra means inside or within. Those two go together. And the other one is called an intermolecular force. And intermolecular forces occur between molecules. And I'm going to add two different molecules. Okay. intramolecular forces are much stronger than intermolecular forces. So intramolecular forces are much, much stronger because those are the ones that are inside that individual molecule. So like I said, we have water on the screen, so it's between hydrogen and oxygen, and they're held together really, really tightly. And so intramolecular forces are much, 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 much stronger. So the strength of intermolecular forces will affect the properties of covalent compounds, such as melting points, boiling points, and so on and so on and so on. And we'll talk more about that later. All right, so intermolecular forces are not discussed when we talk about ionic compounds or ionic bonding because in an ionic bond or compound, they're not really a molecule. So you have to have something that's covalently bonded together. So all nonmetals in order to have intermolecular forces. Okay, so now this is an old slide from a previous unit. So we talked about how, so if it looks a little bit familiar, we have used this exact slide before. So the red arrows are showing us force of attraction. So that would be, you see in the bottom left-hand corner and the top right-hand corner, we have plus signs. And then in the upper left-hand corner and the bottom right-hand corner, we have an electron, which is negative. So we know positives and negatives attract each other. And we know that 2 positives are going to repel and 2 negatives are going to repel. So when forces of repulsion and the forces of attraction between protons and electrons balance at the precise distance where potential energy is at a minimum, then a covalent bond is formed. Okay, so that's when you're going to form a covalent bond. Because remember, they're going to bond because they want to reduce their potential energy and they want to become more stable. That's the whole purpose, is reducing potential energy and becoming more stable. Okay, so the space where the shared electrons are located, this is called the molecular orbital. Oops. Okay, clean that up. All right. Now, so this is a weird diagram. I know, I'm sorry, they are odd, but this shows up in every textbook. So it's showing you in the upper right-hand side, and for whatever reason, you guys on my iPad, I'm not able to point or use like a laser pointer thing on the PowerPoint. So if you look at the upper right-hand side, you have 2 atoms that are separated. They are not bonded together. And the y-axis represents energy, the potential energy. So they are there. They're not bonded with anybody. It's an atom plus another atom. So they have a relatively high energy, and everybody wants to be at a low energy. Lower energy is better. So if you notice if you look at the pair that's at the very, 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 very bottom, that's at the bottom of the dip, these 2 atoms got to be at the perfect distance from each other to where they could bond. Now the pair that's over to the left of those, that's up high, where the x-axis is at a 0, they are too close together. And then the pair that's sort of in the middle of the screen, they're just not quite close enough. They're a little bit too far away. So they're going to be very unstable. So the one that's at the very bottom of the dip, that distance represents the perfect distance for those particular atoms in order to form a bond. All right, so let's summarize this in notes because I don't like the fact that I can't point at stuff on this slide, so we can maybe clarify this later if we need to. So let's see, bond length is the distance between 2 bonded atoms at their minimum. Oops, my pin's not working. Here we go. Minimum potential energy. So for the graph, that's going to be the bottom of that little dip or the bottom of the hill or the hole. All right, so bond energy is the energy required to break a chemical bond. So how much energy do you have to put in to break a bond? It's called bond energy. So when you're forming a bond, atoms release energy. Why? Because they're going to be at a lower energy, so they don't need to have it, so they release it. The same amount of energy must be added to break the bonded atoms. Okay, so when we form bonds, we release energy. That's an S. And when we break bonds, this requires energy, so you have to put energy in. Okay, so let's explain why shorter bonds take more energy to break. Well, we can look at this graph, and when we take a look at it, we can see that on the left-hand side, on the left-hand column of the data table, we have hydrogen bonded to a hydrogen, we have hydrogen to a chlorine, we have chlorine to a chlorine, we have a carbon to a carbon, a single bond, a double bond, a triple bond, and then the same thing with the nitrogen. Okay, so we can notice that the shorter the bond length, which is the middle column, we can look at the bond length, and then we can look over at the far right column where our bond energies are located. So the shorter the bond length, the more energy it requires to break it. So if you think about this, shorter bonds are stronger and more difficult to break. And we're going to demonstrate this in class when we get back in class. But for now, just hang on to that. Now, if you take a look and you think there's a hint right here, which has a really good analogy. If you think of a pencil, it's like a wooden pencil, obviously not a mechanical one. If you have a long, like a brand new pencil and they're long, a longer one, or if you've like used it for a while and now it's gotten really short, it's actually much easier to break a longer pencil than it is a shorter pencil. It's the same thing. If you have a shorter bond length, then it's harder to break them apart. If you have a longer bond length, then it's easier to break them apart. And then you can think about that in terms of double bonds and triple bonds. If you had two pencils together and you're trying to break both of them, that's even harder. And then if you had three pencils together, that's even harder to do. So the longer the bond that you have, and the fewer number of bonds, meaning a single bond, the easier it is to break them apart. Now here's a question, which I'm not going to answer right now because we'll answer that in class. I'm going to make you think about it. So you fill this in, do this yourself, fill it in, think about it. It's supposed to be an arrow, but you know, it's different with an Apple pen or pencil or whatever this is called. So think about this and answer it on your own, and then we will talk about it in class. Actually, you guys are going to think, pair, share when we get back to class. Okay, so now let's move on. Page number 2, the octet rule. All right, so we know this one. This is still review. So covalent compounds form bonds by sharing electrons so that each atom has an outer energy level with 8 electrons. Okay. So the shared electrons form overlapping orbitals so that each atom achieves a noble gas notation or configuration. So remember, those noble gases, they are very satisfied. They have their octet and they are super, 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 super happy if we are going to personify. Okay, so continuing with our octet rule, we need to draw the Lewis structures for these that are on the paper. So we have fluorine, which occurs as an F2 molecule. So each fluorine is in group 7, so they have 7 valence electrons. And so we know that they have the electron configuration of 1s2, 2s2, 2p5, and we know what that orbital notation looks like. And so we can see that they're going to have overlap in that one orbital. So again, like I said, this is review for us. So they're going to look like this. And take note that the bond that is right here, that's being shared. So we draw a line. There's 2 electrons there as well, but we draw the line. All right, so then for our oxygen, who is in group 6, has 6 valence electrons. And it's 1s2, 2s2, 2p4. So when we take a look at the orbital notation, we can see exactly where there's going to be overlap. And since there's only 2 atoms there, it tells us that it's going to end up, they're going to have a double bond. So it's going to be oxygen double bonded to another oxygen, and each one has 2 sets of lone pairs. Again, we have our double bond that's written as 2 lines instead of 4 dots because it's representing that they are shared. And then we have nitrogen, who nitrogen is a group 5 fella, so he has 5 valence electrons. And so he's 1s2, 2s2, 2p3. And so we can see the 3 orbitals, well, there will be overlap. So they are going to have a triple bond, and they have, there we go, the 2 extra dots on each end to satisfy their octet. All right, so we have the triple bond, and again, we draw the lines to show that they are shared. All right, diatomic elements. Don't forget your diatomic 7. Again, this is still review for us. The diatomic 7 are the 7 elements on the periodic table that are most stable in pairs. So everything is about stability for molecules. They will not be found as a single atom in nature. They're going to be in a pair all the time. So make sure you know the diatomic 7. So we have hydrogen gas, we have nitrogen gas, we have oxygen gas, fluorine, chlorine. These are all gases at room temperature. Bromine is a liquid. And iodine, and he's a solid. You don't really need to know that. I'm just sticking that in there. All right, so those are your diatomic 7. And it's a really great hint that we've talked about this before, that you start with, well, you have hydrogen first, and then you start with number 7, atomic number 7 on your periodic table, and then draw or write the number 7. Okay, so you start with hydrogen, and then plus element number 7, who happens to be nitrogen. That's an equal sign, equals nitrogen, and then you write the number 7. So not to make you dizzy, I'm just scrolling to get down to this periodic table. So when you're doing this, you have hydrogen, go to element number 7, and then write a 7. Okay, and so that 7 will tell you these 7 elements are the diatomics. And you need to remember those always, always, always. Okay, so now let's talk about exceptions to the octet rule. And right here on this part of the notes, it's actually missing a little bit as one thing, and I will add it. It pops up later in the PowerPoint. I don't know what happened to it here, but it's okay. All right, so exceptions to the octet rule. Atoms that cannot fit 8 electrons. And then there are also atoms that can fit more than 8 electrons. All right, so I'm actually going to use the space where I'm writing right now to go ahead and summarize this real quick, and then I'll fill in the exceptions at the bottom. So atoms that cannot fit 8 electrons, which means they need less than 8, they're going to be hydrogen, beryllium, and boron. Draw a little line. And atoms that can fit more than 8, that means more than 8. So these are less than 8 and these are more than 8. These are going to be any atom whose energy level is greater than or equal to 3. So anybody that's an energy level 3 or greater can fit more than 8. Not that they want to, but they can. They still want 8. They don't want more than 8. They still want those 8. All right, I'll show you that on a periodic table in just a second. Let's fill in our notes. So hydrogen, it has 1 electron in its s orbital. And so it can only form 1 bond. All right, boron has 3 valence electrons and will only form 3 bonds. And then the main group elements in period 3 and below meaning bigger, below on the periodic table, form what we call expanded octets. And the expanded also means, in this case, bigger. Okay, so let's go down to our periodic table for just a second. All right, so to help you remember that rule, let me get rid of this right here. So this is the easiest way I can think of it. Go to group 1, the top element is hydrogen. All right, he wants 2 electrons, which equals 1 bond. Then go to the top in group 2. Remember, from here on out, electrons occur in pairs, right? So I can't add just 1 electron, I can add a pair. So he wants 4 electrons, which equals 2 bonds. That's beryllium. That's missing in this on this slide, a PowerPoint slide, but it's still there. Let's see. I want a different color pen. Ooh, pink is pretty. And B is, so we have 2, 4, 6 electrons, which is 3 pair. And then we want, let's see, I don't want a highlighter. This will be okay. When I get to carbon, that's 8 electrons, which is 4 pair. And everyone after that wants 8 electrons and 4 pairs. Everyone else wants 4. So let's go through that really quick one more time. If we are the top one in group 1, 2 electrons, which is 1 pair, which is 1 bond. Then the top of group 2, that's 4 electrons, that's 2 bonds, or 2 pairs. Over here in the top of group 3, that's 6 electrons, that's 3 pair, or 3 bonds. And then once I get to the top of group 4, that's 8 electrons, 4 pair, 4 bonds. Everybody else wants the exact same thing. Now, if I am in energy level 3 or greater, so this starts energy level 3. Energy level 3 or greater, all of these elements can, I'm going to fill in right here, can expand their octet. Why? Because when we entered energy level 3, we added the D sublevel. So the D sublevel has room for 10 extra electrons, and so there's space there. So there's an extra space to put the electrons, but your atom isn't going to want to do that. Your atom's going to want to stick with the 8 valence, but it can technically expand its octet if it needs to. Okay, so back here. Alrighty, so now let's talk about covalent bonding. So don't forget, covalent bonding is nonmetal to nonmetal. So these are the elements that are highlighted right here on this periodic table are the ones that are going to be involved in covalent bonding and drawing all these Lewis structures. So let's take a look at the Lewis structure for CH3I. Who's going to be involved? Nonmetals. Okay, so let's go back to our rules really quick from when we were drawing structures the other day with the polyatomic ions. It's the same rules. The only thing that you don't do is put brackets around it because these aren't ions, because they're neutral. So we need to count up all of our electrons first. So I'm going to come over here on the side. And let's get a lighter color since I'll be writing on the black paper. So I have carbon, which has 4 valence electrons, and only one of those. I have 3 hydrogens that has 1 electron each. And I have iodine, which has 7 valence electrons. It has no charge, so I don't need to add or subtract any electrons. All right, so that's going to be 14 electrons for me to work with. Okay, so that's important for me to know. So now, when I come back over here, I need to pick my central atom. I can go look up those electronegativities if I need to, but I'm really paying attention, and I recognize that I have a carbon. And so the minute I have a carbon, I know carbon's going to go smack dab in the middle. That means, and I only have 1 carbon, so I don't need to worry about putting 2 in the middle. Sorry if you hear that noise, that's my dog. I have 3 hydrogens and 1 iodine to add. It doesn't matter. No one ever told you that the atoms that you are adding to that central atom have to be the same type, because they don't. I have to stick on him with the skeletal structure, 3 hydrogens and 1 iodine. Okay, 3 hydrogens and 1 iodine. Carbon goes in the middle because he always does, and then I attach the other atoms to the central atom. Okay, and so when I did that, let's take inventory of the electrons that we just drew. 2, 4, 6, 8. So I just used up 8 electrons. So of my 14, I just used 8 electrons. So let's do some quick math. That means I have 6 electrons left. Okay, so I'm going to come back over to my drawing, and I'm going to take a look at it. And the hydrogens that are here, they don't need any lone pairs because they only want 2 electrons. Each one of those has a bond, which is 2 electrons touching them. They're totally okay with that. So I'm going to go over here to the hydrogen and my iodine. I meant to say iodine. And he's going to need 2, 3, 4, 5, 6 added to him, because he needs to satisfy his octet. So I had 6, I just used 6, I have 0 left. So I'm going to come back and check my atom. Don't forget to check carbon, 2, 4, 6, 8 around him. He is totally happy with that. All right, so he should look like this when we're done. Now, how many lone pairs does he have? Well, how many pairs of lone electrons that are by themselves? There are 3. Where are they? They're right around the iodine. So they are, come on, get off of there. There we go. 1, 2, 3. So we have 3 pairs, which equals a total of 6 electrons. How many shared pairs? Well, we already highlighted those in green, so there are 4, and that's 8 electrons. And we used 14 electrons, which was great because that's what we started with. And so then our next question is, why doesn't hydrogen have any lone pairs? Well, we've answered this question a lot so far in this unit, because hydrogen only needs 2 electrons or 1 bond, because it has only an S sublevel. Doesn't have a P. That's all it has. Okay, so we're moving on. And again, this is a lot of review, so I'm going to just go through it a little bit quicker. Again, the rules, the steps for your Lewis structures. Count the number of valence electrons you need. Then it says set up the skeletal structure. And then after we set up that skeletal structure, the least electronegative is the central atom. If carbon is present, then it will always be the central atom. Hydrogen and halogens, so group 7, I don't really like the word never with halogens, but never for hydrogen. So I'm going to put like a little star on halogen. It's going to drive me nuts in this presentation. But hydrogen definitely will never be a central atom. and halogens usually not, especially the smaller ones like fluorine and chlorine, but they will form single bonds. One single bond. So give all atoms an octet by adding lone pairs. Like we did for the iodine. Check to make sure that all atoms have an octet. The exceptions are going to be hydrogen, also beryllium, even though it's not on the slide, and boron. Count electrons to match the number of electrons required for the compound. Okay, so we've already drawn the CH3I, so we're not going to draw it again because that's a waste of our time. All right, so now let's take a look at C2H4 and C2H2. So I'm going to go ahead and give you a hint. They're going to involve the double and triple bonds, so we got to think about this. So if we take a look at drawing out our skeletal structure, we immediately see we have a carbon. It's going to go in the middle. The issue is I have two carbons. So I'm going to put them here and just connect them. And yes, I needed to go and count them up. Sorry, my bad. So for carbon, I have 2 times 4 plus hydrogen, which is 4 times 1. So 2 times 4 is 8, plus the 4 times 1, which is 4, which is 12 electrons. So for the C2H4, I have 12 electrons. So we're setting up our skeletal structure. Now I have 2 carbons and I have 4 hydrogens. And so some kids are like, I'm not really sure how to place them. Well, nature tends to be very symmetrical. So when in doubt, just go with symmetry. So if I have 4 hydrogens, place around 2 carbons, I'm just going to put 2 on 2. Okay, so then we want to satisfy everybody by they're going to need a lone pair of electrons. So this is not really the way that I do it, but just so we can follow along, they're going to tell us to give everybody a set of lone pairs and then check to make sure that they all have their octet. Count the electrons to make sure they match the required amount for the compound. But when you do that, you realize you actually used 14 electrons. So if you have 2 too many electrons, then you're going to end up with a double bond. All right, so we're going to work this the way that I showed you how to do in class, which is we have 12 electrons to work with as we calculated over here. And I'm just going to put it right here. Let's count what we used. So we used 2, 4, 6, 8, 10. So we used 10 electrons. So I have 2 electrons left. All right, so I need to figure out how I'm going to use those 2 electrons. So if I give them to this carbon here, then he is happy, quote unquote happy, because he has 8 electrons. But the other carbon on the right only has 6, so that won't work. And so if I take those away, and what happens if I put them on this carbon? Also, carbon on the right is happy now, but carbon on the left is not. So we have to take those away. I only have 2 electrons left, which is 1 bond, and I need both of these carbons to share it, right? They both have to share it and take turns. So they're going to have a double bond put in there. All right, so that would be an example of when you have to do a double bond. And then a triple bond is here. So if we have the C2H2, so let's go count up our number of electrons that we're working with. And so just for space purposes, I'm going to get rid of this math so I can use the same space. All right, so I have 2 carbons, so that's going to be the 2 times 4, which is 8. But I only have 2 hydrogens this time, so that's 2 times 1, which is 2. So I have 10 electrons. So then I need to set up my skeletal structure, which carbon is there, so he's going to go in the middle, and I have 2 of them, so I'm going to connect them. I have 2 hydrogens, so I'm going to go with my symmetry and do 1 on each side. Now, the way I prefer to do it is count these up. I just used 6. So I have 10 electrons and I drew 6. So I have 4 electrons left. So 4 electrons left is going to be 2 bonds. But if you take a quick count, this carbon right here, he currently only has 4 electrons touching him. So in order for him to be totally happy and satisfied, he is going to need 4 more electrons. So there's 1, 2, 3, 4. But when I do that, that uses up all of the electrons that I have left over. And so the second carbon is not going to be very happy at all because he's only getting 4. So we have to figure out, well, what happens if I do that? Let's check it. So the hydrogen on the left has 2 electrons. The first carbon that we encounter, which is right here, has 2, 4, 6, 8 electrons. He's good. Second carbon, 2, 4, 6, 8 electrons. He's good. And then this last hydrogen, 2 electrons, also satisfied. All right, so I'm going to click through this to get to the end because I don't particularly care for that. That's how you would figure out how to draw your multiple bonds. And so sometimes figuring out multiple bonds is a puzzle. I was trying to think of the word. It's a puzzle. So let me give you one tidbit that's not in the PowerPoint. So this is going to be important. Which elements can have a multiple bond? So multiple bonds are going to be double and triple. Okay, so multiple bond is a double or a triple. All right, there's a list, and we say C NOPs. Carbon, nitrogen, oxygen, phosphorus, and sulfur. These guys can multiple bond. Do not draw multiple bonds on anyone else. Just them. Only them. This is the list. So don't put multiple bonds on a bromine or multiple bonds on a chlorine or multiple bonds on anybody else. Just these. CNOPs, carbon, nitrogen, oxygen, phosphorus, and sulfur. Those are the ones that can multiple bond, and they can multiple bond to each other. So like we just had carbon, double bond carbon, or carbon, triple bond carbon, or something like that. But you can have a nitrogen with a double bond to an oxygen, or a phosphorus with a double bond to an oxygen, or something along those lines. That can happen, but it has to be, both elements involved, element 1 and 2, they both need to be on this list. So it can't just be any old random element on the periodic table. Okay? All right, I'm going to finish up with this, and then we are going to stop. All right, so honk, which is pretty funny, the honk rule. So the honk rule is just sort of kind of giving you a guideline. Let me click through it so then I can write. There we go. All right, so for your honk rule, what happens is that hydrogen and your halogens really like to form one bond. So your hydrogen's going to form one bond, and like fluorine's going to form one bond, and then he will have 3 lone pairs. And this is what the honk rule is, what makes them very happy. So this is, they get their cake and they get to eat it too. So some of you, we had this discussion in class, and some of you we did not. But here's the deal. Let's say your favorite cake is red velvet cake, but it's your birthday and your mom makes you a chocolate cake. Well, it's your birthday, you're getting a cake. Cake is okay. You like that, you're happy that you got a cake, your mom made you a chocolate one, it's great. Is it what you really, 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 really wanted? No, but you're still happy that you got a cake for your birthday. So how that relates is the fact that you got a cake, that's your octet rule. So the octet rule wins out first. And then if you get your cake and it's the exact kind that you want and you're super, 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 super happy, that's how this works out. That's how the honk rule is. This is what makes them so just perfectly happy. All right, so hydrogen can only have one bond. It can't do anything else. Halogens only want one bond. They can technically take on a couple of the bigger ones can do more stuff, but usually not. they're not one of the CNOPs, but there are some weird exceptions to that rule. All right, so for oxygen, if you think about what his Lewis dot diagram looks like, all right, he looks like this. 2 bonds. Or if he decides to do a double bond, he's going to look like that. Nitrogen, if you think about what he looks like, and his Lewis dot, he looks like this, right? So he can make 3 single bonds, or he can make a single bond and a double, or a triple bond. And then carbon, he looks like that. So he can make 4 bonds. He can make a double and 2 singles. He can make a triple and a single. All right, so this is their honk rule. Honk rule is what makes them so happy. All right, so what that tells you is that carbon does not like to have a lone pair of electrons on him. Will he take it? Yes, because he wants his octet. But is he going to like it? Not so much. He's not going to be happy with that. And if you look at this one, nitrogen, he likes to have 3 bonds and 1 set of lone pairs. Okay, that's what makes him the most happy. Now, will he take 2 lone pairs and 2 bonds? Yes, because it gives him 8. But that's not what he really wants. Same with oxygen. Oxygen can have 1 single bond and 3 sets of lone pairs. That doesn't make them happy, but he does get his 8 octet, so that's, he'll deal with that. All right, so that's the honk rule. Again, what we're doing right here is going over the steps for the Lewis structure. We're not going to do that again because we've already done it. But I want you to work on drawing these. So this is what I want you to have done before you come to class, is draw these. Also answer that question up previously, I think at the end of page 1. And that is it. I will talk about resonance in class. All right, bye guys.